Good news is I'll be spending the better part of the remainder of the semester explaining that to you. So there's that. What's that? Well, here, let me show you one application, right? Before I get carried away here. So, I mean, there are many applications. Let me just say one of them is this. One if A has eigenbasis. All right. In other words, that means that, say, V1, V2, Vn, these are all eigenvectors. All right. With eigenvalues lambda 1, lambda 2, lambda n, then if we take, let me call this basis beta, then if we take the basis matrix beta, invert it, multiply by A, multiply by beta again, like so, then this is lambda 1, lambda 2, lambda n, like that. And this is probably the most important fact about eigenvectors that I can share with you. If we have a basis of eigenvectors, we can use those to diagonalize the matrix. I'm hoping to explain to you in considerable detail how this allows us to simplify formulas for a number of interesting problems. Sometimes directly, sometimes indirectly, but. So that's actually, I said that's an application. That's kind of like a, maybe that's the wrong thing to call it, but that's an important aspect of eigenvectors. So you see why the spectral theorem is so amazing. What does it say about this eigenbasis? It's also orthonormal, right? So I can trade this inverse for a what in that case? Transpose. Even nicer. Let's see here. But two, just eigenvectors appear in many problems from the real world. Yeah. Let me show you a few of those. One kind of problem is called a Markov chain. So the idea, what's that? What is it? I've talked about Markov chain before in here?
Yes.
I did?
Yes.
I did?
Yeah, for the first test, before the first test.
Man, I forgot. I have no memory of that whatsoever. Oh, stink. But so what we have is we have a probability matrix, right? And if we have a probability matrix times a probability vector, then what do we get? We get another probability vector. Let me be specific, if you don't mind. I'll do a 2x2 system. That's enough. So let me sort of, if my probability matrix is something like this, 0.5, 0.5, 0.0, I'll say 0.1 and 0.9. So this is the reason this is a probability matrix is that the sum of the entries in each column is 1. So 0.5 plus 0.5 is 1, and 0.1 plus 0.9 is 1. All right? And then oh, I don't want to have, I'm sorry, guys. I'm thinking of a specific problem I was working out earlier today. Here we just put the state vector. I'm an idiot. This doesn't have to have that. State vector. So, all right, let's see here. We could come up with some kind of storyline. Let's say that this is x and y. Maybe I should use C and D. Or I'll make up my mind eventually here. Okay, there's some sort of virus, and sometimes children become dogs, but then sometimes they can be cured. So like, I'm going to say C is the number of children, D is the number of dogs, and then like, so this is state X, xk, and then this would be, of course, 0.5 C plus 0.1 D, and this would be 0.5 C. I should come up with a less weird example. A 0.9 D. Let's see here. I mean, you could also think of it as like,
Let's just go with the children.
children, dogs. All right, fine. So if this, so this is basically the new number of children,
That's not enough.
and this is the new number of dogs, right? And so every so often, every period of time, the statistics say apparently 50% of the children stay children, and 10% of the dogs turn to children. A little weird. There it is. And then on the other hand, during that same period of time, 50% of the children become dogs, and 90% of the dogs stay dogs. Right? So you could look at something like, suppose originally you have
Always interesting.
10 children and 0 dogs, right? After one period of time, so this is my initial state vector. After one period of time, you have what? You got 5 children, 5 dogs, right? So this is A. What's A squared times x naught? Well, that's A times 5, right? Can you guys work that out for me? Three.
7.
Really? I would have, this is kind of funny. Like, you could usually get decimals in here. The fact that these both worked out to integers is really kind of charming. And what happens if we continue in this way? What's A cubed times x naught? What's that give you? 1.5 plus 0.7, 2.2. And 1.5 plus 6.3 plus 1.5 is what? 7.8. You notice that the total number,
Always add up to 10.
yeah, the total number of children and dogs always must be 10. My interpretation of this would be that there's one half-dog child, right? Some dog-faced boy, as it were.
80% dog, 20% job.
So what happens to what's a to the fourth on x naught? What's that give you?
Still going.
It's harder for me to catch. That's 0.78 plus 1.1.
1.88.
1.88. If I believe you, then we have 8.22.
1, 2.
1, 2. I can't do math. Now, if there's a steady state, what would that mean? Like the limit as n goes to infinity, right, of the nth vector, what should that be? I mean, that would be the limit. No, not necessarily 0. That would be a to the n times x naught, right?
Really?
If there's some steady state vector, we could call that x star, right? Just call it x star. And so what would happen if you take a times x star? What would happen to it? Intuitively speaking, think about this. If there is a steady state vector, it's the same thing again, right? So what is that? In terms of things we introduced today, what is that? This steady state vector for the Markov chain. It's what? Let me be more suggestive in my writing. 1 times x star.
That's the eigenvalue.
Yes. So this is an eigenvector with eigenvalue lambda equals to 1. So if you want to find the steady state solution to a Markov chain, find the eigenvector with eigenvalue 1. So I can actually solve that pretty fast. I just look for 0.5, 0.1, 0.5, 0.9 times the vector, let's say uv, equal to the vector uv again. What's that give me? 0.5u plus 0.1v equals to u, which gives me that 0.4u is equal to 0.1v. In other words, 4 times u is equal to v.
0.5
So if I choose u equal to 1, that says that v is equal to 4. So therefore, uv is equal to 1. What do I do?
Isn't it 0.5 u? 1 minus 0.5.
Oh, is it 0.5 v? Oh, 0. Oh, I'm sorry. You're right. That matters too. So 0.5 v,
So 5u is equal to
5u. 5u is equal to v, so v would be 5 if u is 1. Now this won't work, right? Because we know that we can't just choose any scaling here because of the interpretation. So this means that my x star, which should be a multiple of that, shut up! 2, 8.
210.
2, 8.
B is 5.
What?
B is 5, not 4.
Oh. Really?
It doesn't matter.
It matters. It matters to me. 5. Oh man, now I got to think about this. What do we need to multiply that by to get a sum of? The sum should be 10, right?
Oh, so
10 over 6, right?
2.5, 7.5.
And 10 over 6 times 5. I'm sorry, I got to fix that. Shush. So what is that? That's I can't do math. 5/3? Yeah. And
5/3.
what's that again? 25/3? Yeah, okay. In terms of a decimal, that's about what? 1.6666 and so forth, and what?
8.3333333.
As you can see, we're drifting towards that. And if you take higher and higher power, I mean, we were already pretty close to that, even after four cycles, right? And so as you go on, if you have a probability matrix like this, long-term behavior will be that it goes to the eigenvector with eigenvalue 1 of the matrix. So this is one place, I mean, and this is an interesting question for lots of functions, is there a fixed point of the function? You plug in the point, you get back out the same point. So fixed points are sort of eigenvectors of eigenvalue 1. I will show you in the days to come that we can also understand the formulas for quadratic forms, which would be something like a formula for, like an ellipse or hyperbola, these sorts of things. We'll find nice formulas for those. That has relevance to energy and something called the inertia tensor in classical mechanics. We'll see how to solve differential equations using eigenvectors. We can solve almost any differential equation using eigenvectors, yeah. So there's like really neat connections between this and differential equations. But I think this alone is actually a pretty good motivation for why it's interesting to look at, if you like this sort of thing. But anyway, I have much more to say, but that's it for today. We'll actually prove this in detail one of these days here when I have more peoples. And I'm sorry I forgot to ask